Hello, everyone. Welcome to session 6. Today's topic is drift detection in data. So why is it important? It's important because the data is not stationary, or in other words, the statistical properties of the data changes. So you might build a model based on some historical data at some point in time. And after that, if the statistical properties of the data changes, then your model is not going to be very effective. So typically for supervised learning problem, that manifests itself as increasing error rate as time goes. So we'll be talking about various algorithms for detecting drifts in the data. So before we get to that, we need to go through some concepts and terminology regarding concept drift or data drift. So since this is a broader problem, beyond what our interest is, which is anomaly detection, so we'll be discussing it within that context of that, broader context of machine learning. So essentially, concept drift happens when there is some change in the data distribution. So for example, if it's a supervised learning problem, you have a joint density between X and Y. So X is your feature and Y is your output. And when the mass shifts in that joint distribution, it may affect your model behavior. So to be more precise, for prediction problems, for example, if the posterior probability P of Y in a given X that changes, it means that the classification boundary is changing for a classification problem. So when this probability is changing, it's called real drift. Now remember, machine learning is all about, machine learning really boils down to predicting this probability one way or other. So when that probability itself has changed, your whatever the model was built on is not valid anymore. So that's when you start seeing higher error rates after you deploy a model. Change can also be in the marginal distribution of P of X. That's called virtual drift. It's also known as covariance drift. But typically, when there's a change in px, it'll change in it'll be accompanied by a change in the posterior distribution also, because it'll also change p of y and p of x, unless the px changes in a very specific way. Then in that case, the posterior distribution may not change, but you can rely on that. I mean, generally, it will be accompanied by eventually the changes in the posterior distribution too. So that's what I meant by the last bullet point. Typically, change in px will be accompanied by change in the posterior distribution. And here I've given an example in anomaly detection. When px changes, for example, for robust z-score based anomaly distribution, for example. So what will happen is that the boundary for normal data, that will change. So you have to rebuild the model. Now, as far as how the transition happens when there is a drift, there can be various scenarios. One is, the change happens very rapidly within a short time. And so these kind of drifts are easiest to detect. The second kind is gradual. So the change happens over a period of time. So what happens is it kind of alternates between the old concept and the new concept, and eventually it settles down on the new concept or the new distribution. Incremental is going from the old to the new. It will go through some intermediate concepts or distributions, which are kind of halfway between, midway between the old and the new. The other is recurring, which is not, which is a special case where there may be drift, and there may be drift again, which will bring you back to the old concept or the old distribution. So it kind of alternates between two different distributions. That can also happen. So in real life, the drift can be very complex. It can be the combination of the three types. So it's really it's not as simple as just one of those. It can be combination. And as I said, when it's gradual or incremental, it's more difficult to predict the drift. So once you detect the drift, how do you what's the what action do you take? So one approach is to not bother about detecting drift at all, and just to periodically build your model, which is called a blind method. I mean, it's not recommended, but people might do that. They just assume the worst case scenario that the data is drifting, so periodically they'll retrain and rebuild the model. The other is informed, which is there is a process to detect the drift, and when the drift is detected, only at that point the model is retrained with newer data. So there can be three approaches for. There are actually, as far as anomaly detection goes, there are three modeling approaches. One is called supervised learning, where you build a model with normal data. For example, you might build a model for z-score or robust z-score, and you only use the normal data. That's semi-supervised, and supervised is like a classification problem. You have labels for normal data and anomalous data. But since anomalous data is very rare, it's not very common to do supervised learning for anomaly detection. It's mostly semi-supervised, like I said, using only normal data, or it can be completely model free. So in that case, the data works directly. I mean, the algorithm works directly on the data. Since there is a model involved, you're not training any model, and the algorithm is working on the current data. So there is no issue of detecting drift, because you're not even building a model. So for example, so one anomaly detection, one such anomaly detection algorithm is based on k nearest neighbor. So for example, let's say you have a time series, and you take a segment, you take a subsequence of the data, and you find the nearest neighbor to that. You find another segment which is the nearest to the segment under consideration, and then your anomaly score will be related to the distance to the nearest segment. So that algorithm is not even building a model, right? It's operating directly on the data. So it's model free. So I wouldn't call it unsupervised. Where unsupervised implies you're building a model like clustering. So this is not even unsupervised. It's model free. Sometimes people call it in-memory model, but there are various terminologies. So for supervised learning problem, there may be some issues in detecting drift, because once the model is deployed and it's making predictions, to be able to detect drift, you actually need the actual level of the data as a feedback. So the problem is sometimes if the feedback is available soon after the prediction is made, then you can use supervised drift detection techniques. If the actual level is not available, or it's not available within some reasonable amount of time, then you have to use unsupervised drift detection technique. But the problem is that when you do unsupervised drift detection technique, you're basically just detecting changes in P of X, which does not necessarily imply that there is actually a concept drift. That means change in the posterior distribution. For unsupervised learning problem, obviously, it's much simpler. You're only concerned about detecting any change in P of X. There's no label involved. For example, in anomaly detection, once you detect an anomaly, typically, actual feedback is not available. I mean, if it is available, you can use supervised drift detection. If not, you have to use unsupervised. For unsupervised drift detection, can be categorized into two types based on the granularity of the drift detection. So most of the algorithm will detect drift at a kind of a global level. In other words, it detects drift that involves the complete data space. There are few algorithms that will detect drift locally, only in some subspace of your total data space. So later on, we'll look at an example of that. For example, when you build a model using decision tree, it could be that the subspace that's being referred to by some internal node in the decision tree, only that subspace has drifted. So the advantage of local drift detection is that you don't have to rebuild the whole model. You just rebuild the model for only that subspace of your data. So for decision tree, what you might do is once you detect a drift in an internal node and all the data that flows through that node, you can remove the tree underneath that node and just retrain that subtree instead of retraining the whole tree. So there are some advantages in doing that, but unfortunately most algorithms are not local, they're all global. So you end up rebuilding the whole model. One common thing as we look at all these different algorithms is that drift will be kind of directly proportional to that statistic. But how do you know that whether it's statistically significant or not? So for that, you may have to do some simulation. You may have to collect lots of different values for that statistic, and then build an empirical distribution, and then define some critical value, and then get your p-value. So sometimes these distributions are available, but most of the time they are not. So that means you have to come up with your own empirical distributions and p-values and all that by doing simulation. Some of the algorithms for unsupervised drift detection will only work for univariate data. So in those cases, I have explicitly indicated. Now, I have a long list of algorithms. I'm not sure I'll have enough time to cover them all, but I'll do my best. Anyway, you have access to the Google Doc. You can look at it. By the way, most of these algorithms are cited in this excellent survey paper on concept drift detection. I provided the link at the bottom of this session. Yeah, this one. So if you want more details, you can refer to this paper, and it has list of most of the solutions, I would say 90% of them, and also provides the, has the citation list at the end of this paper. So you can get hold of the actual paper behind each of these algorithms through that survey paper. So let's start off with, so the main concepts are, we have supervised drift detection. That's only applicable for supervised machine learning when the actual label for the data is available after the prediction has been made. And same and the same issue with the regression also. However, if it's an unsupervised learning problem, then you can only do unsupervised drift detection, because there is no label involved. So the first one is called drift detection method, DDM. So if you look at the prediction that's made by a deployed machine learning model, either it's predicting it correctly or it's predicting it wrong. So if you look at that that result, it's essentially it's a sequence with a binomial distribution. For example, 1 might be the prediction is correct, and 0 means the prediction is wrong. So it's basically binomial data with binomial distribution. So what's done in this algorithm is that they calculate the probability of the error rate, and then they calculate standard deviation, and then they also keep track of the minimum probability of error rate and the standard deviation, and then based on some threshold, it detects whether drift has occurred or not. Later on, we'll actually see when you do the demo, we'll see a Python implementation of this. Early drift detection, it's similar, except that it looks at the gap between the errors and the standard deviation, and then detects drift based on that. So your machine learning is making predictions, right? So you can, and once you have the label data, you can turn those prediction into a sequence of ones and zeros. So 1 means might be the prediction is correct, 0 means the prediction is incorrect. So that's why you're able to treat that as a data with binomial distribution. Adaptive windowing, unsupervised drift detection. So what happens is you take 2 sub windows and you essentially scan through your data, looking at different points, and then your null hypothesis is that the 2 sub windows, they originate from the same distribution. So you take the mean of the 2 sub windows. Excuse me, hold on a sec. And based on something called Hoffding bound, you detect whether there is significant difference between the 2 mean values, and then based on that you decide whether there is drift or not. Exponentially weighted moving average concept drift detection. So what this one does is that it's for supervised drift detection. So it uses a exponentially weighted moving average in a forecasting method to predict the error. And then if that prediction is significantly different from the actual error, then we conclude that there is drift. Local drift detection. So this is what I was referring to earlier. So when drift occurs, typically it only impacts a small region of the feature space, not the complete space. However, most algorithms are not able to handle this kind of granularity. So whenever a drift is detected, typically you rebuild the whole model. But with this, like I was saying, for example, you may have a decision tree, and then each node of the tree, each internal node, you can enable a drift detector. And whenever drift is detected for some node, then you essentially remove the whole subtree under that node and just rebuild that portion of the whole of the decision tree. So that means that internal node is referring to some subspace in your feature space, right? So it means that there has been we have drift only in that subspace, and rest of the feature space there is no drift. Let's say you found a drift in only one node. So that means except for that subspace, there is no drift in the data. So this has this advantage that you don't have to rebuild the whole model. So it's definitely is a big plus. KL divergence. So KL divergence is used to find the difference between two distributions. So that means it's useful for us, right? Because we have most of this drift detection, you're always dealing with two data sets. One is some reference or past historical data set, and then the second one is the recent data set. So you get the distributions, the two distributions from the two data sets. Then you find the KL difference or the divergence. And if the difference is significant enough, there is drift. The one issue with KL divergence is asymmetric. It's also known as cross entropy. It's asymmetric. So what you do is because it's asymmetric, because there are like two versions of KL divergence. Depending upon, you have to look at the expression and you'll see. So that means there are two values, right? So which one do you use? I mean, you can either take the average or the maximum of the two. These are some classic two-sample statistical tests. These are all, there are next three of them. They're all based on cumulative distribution. So you have two data sets. The first one, KS. So you have two data sets, and then you have the cumulative distributions for both of them. And then you look at the maximum difference in the cumulative distribution, and then your drift will be related to that. Kramer von Mises CVM. So this one is also based on cumulative distribution, except that it takes a weighted difference between the cumulative distributions, where more weights are given to the central region of the distribution. This one is also cumulative distribution. It takes weighted difference between the two distributions. And in this case, more weights are given to the tail region of the distribution. So this one is based on maximum difference at wherever that happens to be. So, but for the next two, it calculates the difference going over the whole cumulative distributions, not just one specific point. This is another one also based on difference in distributions, but it just takes the regular distributions and then finds the difference between the distributions and aggregates them. And then your higher this difference, more likely you have drift in your data. So if the two distributions are identical, obviously this difference will be 0, right? So that means there is no drift. Relativized distribution discrepancy. It's similar to the total discrepancy test, except that this one is more sensitive to change in the low probability range in the distribution. It takes the difference and then it does some normalization. Because of the normalization, the difference is more sensitive when the probability values are low. Kernel density distribution also based on difference in distribution, except that what it does is that it takes the first data sets and it fits a kernel-based distribution, and then using that kernel-based distribution, it finds the difference with the second distribution. So it's as if it's fitting some distribution with the first one, and then see if the second data set, how well the second data set fits with that kernel-based distribution. If the fit is poor, that means the second data set comes from a different distribution. So that means there has been drift. Fast Hofting drift detection method. So this is for supervised detection. So what we do in this case, we take a sliding window. So here we have our input is a sequence of ones and zeros. Again, 1 means correct prediction, 0 means wrong prediction. So within that window, it calculates the probability of correct prediction, which is basically the ratio of the correct predictions, right? And it also, as you're sliding the window, it also keeps track of the maximum. So when that probability drops below the maximum, and if the difference exceeds some threshold, it means that you're getting more error, so that potentially there is drift. So when this condition is met, that the difference between the probability of correct prediction and the maximum is above some threshold, and this threshold is defined by something called Hofting inequality theorem. You can Google it and take a look at it. It's basically, its purpose is to define the probability of some value exceeding its mean, and subject to some confidence limit. So anyway, you can look at the details. You can look it up. Even Wikipedia has a good page on it. Page Hinckley test. This is for unsupervised drift detection. So what it does, and this is only for univariate data. It calculates the difference between a data value and the running average up to that point, and then it sums that cumulative difference. And when that value becomes large, there's potential drift in the data. I mean, when it exceeds a threshold. Paired learner. So this is for unsupervised drift detection. So the way this thing works is that you already have a machine learning model for based on historical data. So you also build another model based on the recent data, and then you maintain a counter. And then when you're making prediction with the recent data, you have a sliding window. So you slide the window, you build a model, but your model based, it's called stable learner, that's based on the historical data. That doesn't change, that's still the same. So then what you do is whenever the stable learner makes an error in the prediction, but the recent learner does not, you increment a counter. And then you do the reverse. Then you decrement the counter when the reverse happens. So drift occurs when this threshold is, when this count is above some threshold. Shuffling and resampling. So the way this thing works is that you make an assumption where the drift may have occurred. Okay. Then you split your data with respect to that point. Okay. You take the data prior to that point to train a model, and you take the data after that split point as your test data set, and then you find the error. Okay. Then what you do is then you have to repeat this process multiple times. You shuffle the data, and after shuffling, you again split it into a train and test data sets and calculate the error. I repeat that many times, and then you find the average error. If the difference between the error with the ordered data and the average of the shuffled data, if the difference is above a threshold, then there is potential drift. Or in other words, if there is no drift, then the two errors will be more or less in the same range. And that's because if there was actually a drift around that point, that means with the ordered data, the test data set is coming from a completely different distribution. So you expect very large error rate. But when you shuffle it, your error rates will be smaller, right? Because you're shuffling the data. So you will see the significant difference between the errors in between the two cases. And that means there is drift. This technique is also known as permutation method in the concept drift literatures. Adaptive cumulative windows model. This is for unsupervised drift detection. So this one is interesting. So like I mentioned before, KL divergence is basically asymmetric. When you calculate KL divergence, you can calculate two values from two different distributions. Now, when there is no drift, the two values will be more or less same. There will be very little difference between the two. But when there is drift, you will find that the two values are significantly different, and that's how you detect drift. So it essentially leverages that asymmetric nature of KL divergence, except that when the data sets come from the same distribution, then it's not asymmetric, then it's basically symmetric. Abrupt concept drift detection. So this has two parts to the solution. One is it takes the first of all, it takes the mean vector and the covariance matrix for for the two data sets. And then for the mean vectors, it uses something called, you can look it up, Hotelling, t-square statistics, to find if there is any significant difference. And using the covariance metrics, it uses something called box-M statistics to see if there is any significant difference. If any of them is true, whether it's based on the mean vector or the covariance metrics, then there is drift. PCA based. What you do is, you have multivariate data, so you do PCA. So PCA essentially does dimensional reduction, right? And it'll find, it'll define your data in a reduced dimension space. And each of those dimensions are kind of independent of each other. So with this approach, what you do is you take the difference between the two most significant eigenvectors. So you have the two data sets, you do PCA on both. Then from each data set, you take the most significant eigenvectors. That means the vector with the highest eigenvalue. And then you find the distance between these two vectors, which could be a cosine distance or something. So if the distance is large, that means there is concept drift. This is also based on PCA, but the approach is slightly different. So you reduce your data to lower dimensional space. And then once you have done that, you can treat each dimension as independent, one-dimensional data. And then you can apply any concept drift detection for one-dimensional data. And then you have to repeat that for all the dimensions. So if you find concept drift in one or more dimensions, that means you have overall concept drift. This is autoencoder dimension reduction. It's same, except that you use autoencoder instead of PCA. And the advantage of the autoencoder is it's nonlinear, so it's more powerful. So it's kind of like nonlinear PCA. Otherwise, the technique is same. You do dimension reduction, and then let's say you have two data sets, and let's say you reduce the dimension to 3. Let's say your original dimension was 10 or something. So that means for each dimension you have two data sets, right? The reference data set and the recent data set. So you can apply any concept detection. You can apply any concept detection technique for one-dimensional data. So this one is based on unsupervised drift detection, density difference, based on the square of the density difference. So it's again based on distribution, but it takes the difference and takes square of it. So this is very similar to the another one that we looked at earlier. Local drift degree. This is unsupervised drift detection. So this is again a local drift detection algorithm. So what it does, the basic idea is that you take your feature space and you consider different subspaces. And in any given subspace, for any data set, you take the ratio of number of data points you have from that sample to the total number of data points in that sample. And if that ratio is different between the two data sets for that same subspace, it means that in that subspace there is a drift, only in that subspace. So you have to repeat that for many subspaces, and that way you can find drift locally in your feature space. Linear 4 rate. This is similar to the drift detection for some supervised learning problems we went through earlier, except that it uses 4 metrics instead of just 1 metric accuracy. It uses true positive rate, true negative rate, positive prediction rate, and negative prediction rate. If any of those deviate significantly from normal values, drift exists. So it looks at 4 different metrics instead of just 1. This is an approach which is based on an ensemble of detectors. So it will deploy multiple detectors, for example, DDM, EDDM, with maximum diversity as far as the different kinds of drifts the algorithms can detect. By the way, the different kinds of drifts we discussed earlier, like the abrupt, gradual, and incremental. So not all algorithms will work equally well for all those 3 cases. So some algorithms may work very well for one. Generally, they all work well for the abrupt one, but for the gradual and incremental, some will work well, some will not. So what this thing does is that it chooses a set of algorithms so that all those different cases are covered. So that's what they mean by diversity. So whenever in that ensemble, when any member detects a drift, that's recognized as a drift. So it's not majority vote. It's just any. It's not consensus. It's just anyone. And the reason for that is that each of these algorithms are doing different kinds of drift detection. So that's why it's based on. That's why consensus is not used. Drift detection ensemble. This is also ensemble based, except that the consensus is defined by some minimum number of detectors that needs to detect drift. So the issue arises whenever you're doing some kind of consensus, because you're looking at data over some time scale, right? So one algorithm might detect a drift at time t1, another one might detect a drift at t2. So how do you build consensus when it's not happening exactly at the same time? So for that, they define a small window. So within that small window, if there is consensus, then there is drift. So the next set of algorithms, they're called hierarchical, because it's like what we went through is based on ensemble. And the next few algorithms are hierarchical or staged. So for example, there is a first stage. In this case, for example, it does exponentially weighted moving average based drift detection. And then in the second stage, it is kind of for validation. Only if the first one detects drift, the second stage will trigger, and it will do KS statistic based drift detection. Only when it passes through both stages, drift is recognized. This is another hierarchical one. First stage uses LFR. Remember that list linear 4 rates, the 4 different classification metrics. And then if the drift is detected, it's validated by second stage, which is based on resampling or permutation, which we looked at earlier. So they're architecturally, they're all same. There is a first stage and second stage, except that they deploy different kinds of detectors in the different stages. First stage here is classification accuracy. If the drift is detected, in the second stage, it uses resampling or permutation-based detector. This one is interesting. It's called virtual classifier. So it can be used for supervised drift detection. So what you do is, if you consider a point around which you think there might be drift, so what you do, you take the data set left of that point and you take the data set right of that point. Then you create a artificial classification label. So for example, you might assign 1 to the first data set, that means 1 to the left, and then -1 to the next. And then so basically you have labeled data. You can use that as training data and build a classification model. Now, if there is no drift, then the classification accuracy will be sorry. If the test accuracy is around 0.5, there is no drift. That's right. Yeah. So when the accuracy is high, that means the data set on the right originates from a different distribution. So that means there is drift. There is concept drift. Otherwise, if there is no concept drift, accuracy will be poor, because what you're doing, you have the data sets coming from the same distribution, but you're artificially assigning different levels to them. So you can never build a successful classification model because the two data sets are same. So that's why your error rate will be close to 0.5. Nearest neighbor count. So this also can be used like a local drift detector. So what you do is, you can either do it over all the points in your data space or over some selected set of points. So you have two samples. Okay. What you do is you find the k nearest neighbor for any data point, and out of those k, you count how many neighbors are from the same sample. Okay. Now, if the two data sets come from the same distribution, on an average, that number will be half of k, right? But if the two samples come from very different distributions, then k will be large. And that's how it detects drift. Because if the two distributions are, if the two samples come from two different distributions, then you take the neighborhood of some point. Most of the points will belong to the same sample as the point under consideration, right? So that value will be large. And that's how you detect drift. And also, this is a local drift detector. So you can repeat this for all the data points, or you can do some sort of a grid search. Like you can break up your whole feature space into grids, and then for each grid, take one representative sample and calculate this quantity. Like the number of neighbors that come from the same sample. That will tell you, that will identify you the regions where there is drift as well as regions where there is no drift. So it's a local drift detection technique. So this is the paper through which you can get the most of the citations, most of them, not all of them, because some of them come from other sources. Like this virtual classifier, you won't find that cited here. Anyway. So I'm going to, oops. Show you some demo for this session. So the first one is, the first example is for unsupervised drift detection. So we'll be looking at some sales data, hourly sales data, and then that sales data has undergone, significant drift. Actually, it has gone downward because it happens in retails a lot. Some product might be cannibalized by another competitor product, or there may be some price increase, and that could bring the demand down. So there can be various reasons. And so let's say you have deployed some anomaly detector based on sales data. You want to be notified when there is a significant drop in sales from normal data. And you may have built some anomaly detection model, and you're doing your anomaly predictions. But if the data undergoes concept drift, then you are interested in knowing about that, because you may have to rebuild your anomaly detection model. So this implementation is on Spark. So it uses that statistics called CMV, remember? Based on cumulative distribution, and it looks at the weighted difference between the two cumulative distributions. So I'm just showing the output here. So this is the sales data, and the red regions are where it's detecting drift. See, it's shifting downwards, and then it's staying there. And this is the Scala implementation of that. You can use through configuration, any of the 3 2-sample statistics that we looked at. For example, let's go back. So that implementation supports these 3. This one, and this one. And you can choose the algorithm through configuration. So the result I was showing you happens to be with using this algorithm, CVM. The next one is classification error, and we are using the DDM algorithm. And so I artificially created some data where initially the data had, this is a classifier output. Initially, it had an error rate of 0.1, and then it jumped to 0.2 at some point. So this thing is showing you exactly where the jump is. So that's where the concept drift happened. And this is a Python implementation. It's here. So I started this Python class for unsupervised drift detection. So far I just have one algorithm implemented. So I'm planning to add, few more, as many as I can. So this is the DDM data. Remember, that's based on error rate and the standard deviation of the error rate, based on the binomial distributions and all that. So that's what this thing does. So we only have a few minutes left. So I'm going to wrap it up there, and let's see if there is any Q&A or anything. Okay, no open questions. I know this was there are a lot of content and it was very dense. I couldn't help it because this is a fairly generic topic in machine learning, so I had to it's not just anomaly detection, and I had to do justice to that. So that's why I had to cover a lot of ground, and 1 hour is definitely not enough. But hopefully it's a good survey, and then you can look up the details by following up on the original papers if you want to explore some algorithm in details. So I'll just see if there's anything else I'd like to add. No. Also, this whole topics, this concept drift detection and retraining and rebuilding model, it also comes under the broader area of what's called ML ops. It's kind of the operational aspect of machine learning, like deploying a model and taking care of all the relevant issues. So this is one of the significant deployment issues for machine learning models, concept drift. So, I mean, once you deploy a model, you have to keep constantly monitor it using, any of these algorithms, and then rebuild and redeploy a model once a drift has been detected. Q&A. All right, thank you. All right, thank you.
So yes, we will be sharing the notes for each of these sessions. We have shared the Google Doc. Also, we have placed the GitHub link also there. And in the same documents, you can also find recording for the previous sessions. And if at all, if you come across any other questions or queries regarding this learning series, you can always reach to us at info@elephantscale.com. And since it's holidays coming up, we will have the next session scheduled for Jan 8th, and the last one will be for Jan 22nd. So yes. What is the GitHub link? You can, yeah. I'm just putting it here on the chat window. It's available in the Google Doc. It's mentioned in the Google Doc. The link is there. So, yes, please. So I hope that's it to the questions there. But if anyone wants to still ask a question, or if you come up with a question, please do feel free to send us a message and we can take it up in the next session as well. So yeah. So Pranab should we give it a call now?
Yeah, I think we are done. Thank you everyone for attending.
Yeah. Thank you so much, Pranab. Thank you very much. Thank you,
Sure.
everybody. See you.
Okay. Bye-bye.